Hello friends, welcome back to my YouTube channel. In this would be 13th part of my discussion on liquid extraction. And today I'll be talking about stage-wise liquid extraction with insoluble liquids. So in this case, when you have the feed solution that is containing A and C in it, and the extracting solvent is B. So by insoluble liquids, I mean we are going to discuss a case where A and B, they are insoluble. So in this case, A and B are the insoluble liquids. So in my previous video, I have discussed how you can represent the ternary equilibria when you have this situation. When you have insoluble liquids, then A and B, they are insoluble in each other. I hope you have seen that video. I'm giving a link to the playlist, entire playlist of my videos on liquid extraction. It is available in the description section. You can please watch those videos. So today we will understand single stage liquid extraction that involves insoluble liquids. What are insoluble liquids? I have just told you. So the single stage extraction. Today we will be discussing single stage liquid extraction involving insoluble liquids. So let us begin the discussion. First, let us know more about stage-wise contact. So stage-wise liquid extraction. In stage-wise liquid extraction, the two insoluble liquid phases, they are contacted in a stage-wise manner. And since they are contacted in a stage-wise manner, this stage-wise liquid extraction, it is carried out in a stage-wise contact equipment. So the stage-wise contact equipment will be having number of stages, and the liquid extraction will then be carried out in these stages. Each stage in the stage-wise contact equipment, it must have a provision to intimately mix the two influable liquid phases. This is one case. And it should also have a provision to physically separate the resulting raffinate and extract phases. So every stage in a stage-wise contact equipment that is to be used for stage-wise liquid extraction, every stage should have these two provisions. First, it should have a provision for intimately mixing the two insoluble liquid phases, and then it should also have a provision to physically separate the resulting raffinate and extract phases. So therefore, due to this requirement, each stage in the stage-wise contact equipment, it is formed from a mixer and a settler. So each stage, it is constituted of a mixer and a settler. So let us understand this with the help of this schematic diagram. So you have a mixer which is followed by a settler, and this combination of these two devices, it forms one stage in this equipment. So feed is admitted to the stage, solvent is also admitted to the stage. So the two liquid phases, they will be mixed in the mixer, and then the resulting mixture will be transferred to the settler, where the mixture will be allowed to settle into raffinate and extract phases, and finally the raffinate and extract phases, they will be removed from the stage. So this would be an ideal stage when the raffinate and extract phases, they are in exact equilibrium with each other. In reality, they will go close to the equilibrium, and the efficiency of this stage will tell you how close the two phases are, how close to equilibrium are these two phases, raffinate and extract phases. That will give the efficiency for the stage. Okay, so we must understand that in stage-wise liquid extraction, it will be carried out in stage-wise contact equipment. Each stage in the stage-wise contact equipment should have provision to intimately mix the two insoluble phases it should also have a provision to physically separate the resulting raffinate and extract phases. And this can be easily understood with the help of this schematic diagram. So a combination of mixer and settler forms one stage in the stage-wise contact equipment that is used for carrying out liquid extraction, stage-wise liquid extraction. So let us continue. Now let us talk about the single stage liquid extraction operation. We are going to represent it. Before that, let us understand what is the ternary system that is involved. I have already briefly discussed it at the beginning, but let us understand it in detail. The ternary system involved has three liquids, A, B and C. In this case, liquid C is the solute, and it is soluble in both A and B, whereas A and B, they are insoluble in each other. And these are nothing but the insoluble liquids that we are talking about. These are insoluble liquids. Insoluble liquids. These are insoluble. Like C and B are insoluble in each other. The feed in this case, as you know, this is a solution of A and C, where C is the solute to be recovered. The solvent that is to be used, it is B. If it is pure solvent, it will be just B. But if you are using a recovered solvent, it will contain little amount of C in it. So if it is a recovered solvent, then it will be B plus little amount of C. Then the feed solution and the solvent, they are contacted with each other in a single stage operation. We are discussing this operation where the two insoluble liquid phases, they are contacted in a single stage. So this operation you can carry out in a batch-wise manner, or you can carry out in a continuous manner. So the single stage liquid extraction that we are talking about, it could be carried out, it could be a batch-wise operation, or it could be a continuous operation. Okay. Now let us represent the single stage liquid extraction. Single stage with the help of this circle. This is stage number 1. There is only one stage in the operation, as the operation is a single stage operation. Feed is admitted into the stage. Feed will be containing A and C in it, and I'll shortly tell you what are the C of XF, small xf and capital XF. So the feed solution, it is contacted with solvent. If it is pure solvent, it will be just B, and if it is recovered solvent, it will be B plus little amount of C in it. So the solvent is also admitted to the stage, and there will be intimate mixing of the two liquid phases. The resulting mixture will be allowed to settle, and then finally the mixture will settle into raffinate and extract phases, and these two phases will be removed from the stage. So you have the raffinate phase, it will be containing A and C in it, and then you also have the extract phase, which will be containing B and C in it. I will tell you what are R1, X1 and even Y1. Now, the thing to be remembered in this case is, since A and B, they are insoluble in each other. Since they are insoluble, all of the A, it will remain in the raffinate phase, and all of the B, it will remain in the extract phase. No B will go to the raffinate phase, and no A will go to the extract phase. All A will remain in the raffinate phase, and all B will remain in the extract phase. That is the different thing that you have to note for this operation, because that is going to change the way we analyze the operation. Okay, so in a single stage operation, feed, it is contacted with solvent to produce raffinate and extract phase. Now let us understand what are the terms, what are the notations that we will use. So for feed, F is its mass or mass flow rate. Mass if it is a batch operation, mass flow rate if it is a continuous operation. Then small xf is weight fraction of C in the feed, and capital XF is weight fraction of C on a C free basis. So I have discussed what are these concentrations? Weight fraction of C on a C-free basis. That is weight fraction of solute on a solute-free basis. I have discussed these concentrations in my previous video. You please watch that video. Then for solvent, S10 is the mass of the solvent for batch-wise operation or mass flow rate for continuous operation. Then YS is weight fraction of C in the solvent phase, and then capital YS is weight fraction of C on a C-free basis. Then for raffinate phase, R1 is its mass or mass flow rate, depending on whether it is a batch-wise operation or a continuous operation. Small x1 is weight fraction of C in it, whereas capital X1 is weight fraction of C on a C-free basis in the raffinate phase. Then for the extract phase, E1 is its mass or mass flow rate. Small y1 is the weight fraction of C in the extract phase. Capital Y1 is weight fraction of C on a C-free basis in the extract phase. So this is a description of all the notations that I have used in this particular discussion. You have to remember, in this case, since A and B, they are insoluble in each other, all of the A will remain in the raffinate phase and all of the B will remain in the extract phase. Okay, so let us move ahead. So again, we will take the schematic diagram into our discussion. So when you mix the feed solution with the solvent in the stage, so when the feed solution is mixed with the solvent, what happens? It produces a mixture. And then this mixture, when it is allowed to settle, it will settle into raffinate and extract phases. So when the feed solution is mixed with the solvent, it will first produce a mixture, and when this mixture is allowed to settle, it will separate into extract and raffinate phases. And after separation occurs, these two phases will be physically separated from each other. Now let us write total material balance. Total material balance for this operation, and we are going to write steady state total material balance for this operation. So steady state material balance, it will be feed is mixed with solvent, so F plus S10, that produces a mixture M1, and then this mixture separates into extract and raffinate phases. So in this equation, M1 is nothing but mass or mass flow rate of the mixture that is produced when you mixed the feed solution with the solvent. Then from this, we can write two equations. One is F plus S10 is equal to M1. I will call it as equation number 1. And then the other one is R1 plus E1 is equal to M. So this equation is also possible. We can write this equation as well. R1 plus E1 is equal to M1, and I'm calling it as equation number 2. So by taking total material balance for this stage at the steady state, we are getting equation 1 and equation 2. Okay, so after writing the total material balance, now let us write down material balance for solute C. Material balance for the solute, and we are going to write it at the steady state. Material balance for the solute at the steady state, so it will be written as F into XF plus S10 into YS, that is feed into weight fraction of the solute, plus solvent into weight fraction of the solute, that is equal to mixture into weight fraction of the solute in the mixture, that is equal to raffinate into weight fraction of solute in raffinate, plus extract into weight fraction of the solute in the extract. So material balance written for the solute at steady state gives us equation number 3. I am calling it as equation number 3. So it is F into XF plus S10 into YS total into fraction of the solute. That gives us material balance for the solute. F into XF plus S10 into YS, that is equal to M1 into XM1, that is equal to R1 into X1 plus E1 into Y. Well, let us call this as equation number 3. In this case, xm1, as I said, this is weight fraction of C in the mixture. Now, we will analyze each of the stream that is involving the operation. So you have the feed, then you have the solvent, and then you get raffinate and the extract. Now let us first look at the feed solution. We know feed solution, it contains two components, A and C. That means total feed, total mass of feed is equal to mass of A plus mass of C. And how do you get mass of C in the feed? It will be F into XF. Total mass of feed into fraction of solute in it. So that's why I can write F is equal to A plus XF into F. So that XF into F will give me mass of C present in the feed. So mass of feed is equal to mass of A plus mass of C. Mass of C is given as weight fraction of C in the feed into the mass of feed. So in the next step, I will write the equation in this way, F minus XF into F, that is equal to A. So this term I have brought on the other side. And now in the next step, I can take F common on the left hand side. So it will be F into 1 minus XF, that is equal to A. That is F is equal to 1 upon this term. When it comes on this side, it will be F is equal to 1 upon 1 minus XF into A. Now in the next step, I will multiply, let me erase it. In the next step, I will multiply on both the sides of this equation with XF. So it will be up into XF, that is equal to XF upon 1 minus XF into A. And in this equation, the term XF upon 1 minus XF, it is nothing but capital XF. What is capital XF? This is weight fraction of C. Weight fraction of C on a C-free basis in the feed. On a C-free basis in the feed. That means in this equation, this term XF upon 1 minus XF, it can be replaced with capital XF. What is capital XF? Capital XF is weight fraction of C on a C-free basis in the feed. So if I do this, I will be getting this equation, F into XF, that is equal to capital XF into A. That means the term F into XF in equation number 3, it can be replaced with XF into A. Why this is possible? This is possible because A and B, they are not soluble in each other. Okay, so let us that what we have understood, we can replace the term F into XF with capital XF into A. What is capital XF? Capital XF is defined in this way, and this is weight fraction of C on a C-free basis in the feed. Now, let us analyze the solvent phase. Solvent, it contains B and C. If it is pure solvent, it will just contain B in it. But if you are using a recovered solvent, then it will also contain little amount of C in it. So that means S10, mass of the solvent S10 is equal to mass of B plus mass of C. And how do you write mass of C in the solvent? It will be S10 is equal to B plus Ys into S10. Fraction, weight fraction of C in the solvent into mass of solvent. So in the next step, I will bring this term on this side. So it will be S10 minus Ys into S10, that is equal to B. Now in the next step, I can take S10 common on the left hand side. So it will be S10 into 1 minus Ys is equal to B. So that is S10 is equal to B upon 1 minus Ys. Now I will multiply with Ys on both the sides. So it will be S10 into Ys, that is equal to Ys upon 1 minus Ys into B. And in this case, this term Ys upon 1 minus Ys is nothing but capital Ys. What is capital Ys? This is weight fraction of C on a C-free basis in the solvent phase. So that means this term can be replaced with capital Ys, and that is what I will do in the next step. So it will be S10 into Ys, S10 into small ys, that is equal to capital Ys into B. So that means the term S10 into Ys that is present in equation number 3, it can be replaced with Ys, capital Ys into B. So we are going to do this. We are going to replace each term with a term that will be containing capital X and capital Y. For time being, now it is clear that the term S10 into Ys, it can be replaced with capital Ys into B. Now let us analyze the raffinate phase. Raffinate phase, it will contain A and C in it. There will be no any other component in it. That means mass of raffinate will be mass of A plus mass of C. That is, mass of raffinate is equal to mass of A plus x1 into R1, because that will give mass of C in the raffinate. So in the next step, I will write R1 minus x1 into R1 is equal to A, and now you can take R1 common. So it will be R1 into 1 minus xa, that is equal to capital A, that is R1 is equal to 1 upon 1 minus x1 into capital A. Now I will multiply on both the sides with x1. So it will be R1 x1, that is equal to x1 upon 1 minus x1 into capital A, and the term x1 upon 1 minus x1 can be replaced with capital X1, which is weight fraction of C on a C-free basis in the raffinate phase. So if we do that, we'll be getting R1 into small x1, that is equal to A into capital X bar. That means the term R1 into x1 in equation number 3, it can be replaced with A into capital X1. Now let us look at the extract phase. Extract phase will contain B and C in it. So that is, mass of extract is equal to mass of B plus mass of C. That is, mass of extract that is equal to mass of B plus Y1 into E1. Weight fraction of C in the extract into mass of extract, that is nothing but mass of C. So that is E1 minus Y1 into E1, that is equal to B, and then we can take E1 common. So it will be E1 into 1 minus Y1 is equal to B, that is E1 is equal to 1 upon 1 minus Y1 into B. Now let us multiply with Y1 on both the sides. So it will be E1 Y1 is equal to Y1 upon 1 minus Y1 into B. And now Y1 upon 1 minus Y1, it can be replaced. This is nothing but capital Y1, that is weight fraction of C in the extract phase on a C-free basis. So it will be E1 Y1 will be equal to B into capital Y1. That is, the term E1 Y1 in this equation can be replaced with B into capital Y1. So in this way, we have got replacement for each term in equation number 3. F into small xf, it can be replaced with capital Xf into A. We are going to do that. Then S10 into small ys, we are going to replace with capital Ys into B. Then R1 into small x1, we are going to replace it with A into capital X1. E1 into Y1, we are going to replace it with B into capital Y1. So if you do that, equation number 3 now will be written as xf into A plus ys into B, that is equal to A into capital X1 plus B into capital Y1. I am not included this term m1 into xm1. I have equated this part with this part, where now we have expressed every term in terms of capital X and capital Y. So it is capital Xf into A plus capital Ys into B, that is equal to capital A into capital X1 plus B into capital Y1. Now in the next step, what we will do, we will collect terms containing A on one side and terms containing B on the other side. So if we do that, it will be Xf into A minus A into X1, that is equal to B into Y1 minus Ys into B. Then in the next step, you can take A common on the left hand side and B common on the right hand side. So it will be xf minus x1, that is into A, that is equal to capital Y1 minus capital ys into B. That is A upon B is equal to Y1 minus ys divided by xf minus x1. So the equation that we have obtained, it will represent a straight line on the xy plot. On the xy plot, it will be a straight line, and endpoints of this straight line according to this equation are xf ys and x1 y1. Now what we will do, we will rearrange this equation so that you are subtracting, let us say you are subtracting, if we say that this is point number 2 or point number 1, in number 1, and this is in number 2. So let us rearrange the equation so that in the numerator you have 1 minus 2, and in the denominator also you have 1 minus 2, or 2 minus 1 in the numerator and 2 minus 1 in the denominator. So if I have to do that, what will, in the numerator it is y1 minus ys, that is point number 2 minus point number 1, divided by, over here it is 1 minus 2. Now let us make it 2 minus 1. So I'll have to interchange the position. I'll have to multiply with negative sign. So that negative sign will come on this side. So that's why you have minus a by b. So it will be capital Y1 minus capital Ys divided by capital X1 minus capital XF. So this is the equation of a straight line which has a slope of minus a upon b. The slope of the line is minus a upon b, and this is nothing but the operating line for this single stage liquid extraction operation that involves insoluble liquids. So for this line, slope is minus a upon b. So it is a line of negative slope, and it will be having the endpoints xf ys and x1 y1. So these are the endpoints. And what is the slope? Slope is minus a upon b. So we will show this line. I'm going to show the line on the xy plot. But time being, you please note that the equation for operating line of a single stage liquid extraction operation involving insoluble liquids, it is minus a upon b, that is equal to capital Y1 minus capital Ys divided by capital X1 minus capital Xl. Represented on the xy plot. So for that, we will plot capital Y on y-axis and capital X on x-axis. I have discussed about this ternary equilibrium diagram in my last video, in my previous video. You please watch it. So you are going to get the equilibrium curve. And now we will be plotting the operating line which has this equation. Minus a upon b is equal to capital Y1 minus capital Ys divided by capital X1 minus capital Xl. So endpoints, which points, the endpoints, we had noted the endpoints. One endpoint is xf and ys, capital Ys. So in any operation, both will be known to us. The feed composition, weight fraction in the feed and weight fraction in the solvent on a CFE basis, they will be known to. So we are going to use this point to, the operating line will start at this point. So what we will do, we will locate Ys and then we will locate xf. We will get this point. Now it is confirmed that the operating line will be starting at this point, but it would be a line of negative slope because slope of the operating line is minus a upon b. So the operating line will look like this. It will be having a slope of minus a by b, minus a upon b. And when you extend it to the equilibrium curve, you get this point. This is the other end point, which has the coordinates of x1, capital X1, capital Y1. Okay, so this end point will give us capital X1 and it will give us capital Y1. Okay, so once we have done this in order to get X1 and Y1, and now you know how to get X1 and Y1. For that, we need to plot the operating line of the desired slope. The operating line starts at xfys and it will end on the equilibrium curve at x1, y1. So we have to read the coordinates of this point, coordinates of the other end point to know the values of y1 and x1. And we are going to use those values for calculating r1 and e1. So x1 and y1 are now known. Equation 2 that was written previously, the equation is r1 plus e1 is equal to m1. That is one equation in r1 and e1. First, we are going to find these quantities. Then equation number 3 is f into xf plus s1 into ys. That is equal to m1 into xm1 is equal to r1 into x1 plus e1 into y1. So this equation can be written as f into xf plus s1 into ys. That is equal to m1 into xm1, and then from this you can calculate xm1. xm1 will be equal to f into xf plus s1 into ys divided by m1 from this equation. That is, after calculating xm1, this product will be known to you, and then you can write the other equation in terms of r1 and e1. So it will be r1 into x1 plus e1 into y1, that is equal to m1 into xm1. So this is another equation. In r1 and e1, x1, y1, they are known to you because we are going to get them from capital X1 and y1. I'll tell you. Okay, so we have got the two equations. r1 plus e1 is equal to m1. r1 into x1 plus e1 into y1, that is equal to m1 into xm1. Now, in order to use small x1 and y1, small y1 in this equation, you can get those by using capital X and capital X1 and capital I1, because small x1 is equal to capital X1 divided by 1 plus capital X1, and small y1 is equal to capital Y1 divided by 1 plus capital Y. I have derived these relations in my previous video. You please watch it. So that means when capital X1 and capital Y1, they are known, we can convert them to small x1 and small y1, and that will give us the second equation. In second equation, everything will be known to us except r1 and e1. So you have two equations, you have two unknowns. Which are those two unknowns? r1 and e1. So solve these two equations simultaneously and get the values of r1 and e1. In this way, you can get the values of r1 and e1 in this single stage liquid extraction, which involves insoluble liquid. So with this, I end my discussion for this video. In my next video, I'll be solving a numerical based on single stage liquid extraction, which involves insoluble liquid. So thanks. With this, I end my discussion for this particular topic. Thanks for watching the video. Do subscribe to my channel. Tell your friends to subscribe to it and hit the bell icon so that you will be notified as soon as I upload any new video on my YouTube channel. If you have any suggestions, if you have any doubts, if you have any feedback, you please give that in the comment section. For now, have a nice day. Thanks for watching, and I'm sure you'll join me in my next video, where I'll be discussing a numerical that is based on single stage liquid extraction that involves insoluble liquids. Thank you. Have a nice day. Bye bye.